Hello, everybody. It's very nice to welcome you here at this first meeting of the WOST QISS seminar series, which is a continuation of the QISS seminar series that most of you are familiar with. But now they continue within the framework of the new project without space-time, or WOST, which is led by Francesca Vidotto and Flaminia Giacomini. This seminar series will be coordinated by Mushin Han, Philip Hyun, and myself, Ognian Oreshkov. And the idea is that they will happen typically about once per month. And the format is roughly that there will be a presentation for about 40 minutes, followed by plenty of time for questions by the audience. The topics are topics at the intersection of quantum foundations, quantum information, and quantum gravity, as well as philosophy of physics, in the same spirit as the seminars of QISS. So, after these preliminary words, I'm happy to just pass the screen to our speaker, Renato Renner, who will talk about black hole paradoxes and Wigner-Frank paradoxes. Renato?
Okay, thanks, Ognian, for the introduction. That's, of course, an honor to start this new seminar series. But I also wanted to thank everyone who was actually contributing to organizing this whole new enterprise, WOST. It feels like a big challenge to actually live up to the expectations, to unify everything that you just mentioned, to bring together quantum information, quantum foundations, and quantum gravity. But I will give it a try, and I'm really thankful for the opportunity to talk here and hopefully contribute to the scientific discussion. It's also very nice to see so many familiar faces here, or those who haven't their camera on to see familiar names. So I'm very glad to be here. And I'm not sure how this is usually organized, but I'm happy to also answer urgent questions during the talk. Maybe for the more, let's say, discussion type sessions, I would probably prefer if this is at the end. But if there's something that is not clear, I would prefer to immediately clarify it if possible. So let me try to share the screen again, so that you can see my slides. Okay. Now there's also, I hope the setup works like that.
Looks good.
Okay. Okay, so I will actually talk about work which really has the purpose of bringing together quantum foundations and quantum gravity, as you can see from the title. Wigner's friend type experiments are experiments that keep the quantum foundation community quite busy until today, or one could say even more today. There has been recently quite some enthusiasm about finding new types of such experiments and so on. And I will also explain a bit what this meant, what new insights quantum foundations can offer. But let me first start with the gravity side. And those who have heard talks from me before have maybe seen that I call that a cosmic scattering experiment. So the experiment is basically consisting of an agent. I always use agents, you can see later why, who prepares a huge shell of matter. So that's this white thing. You can think of it like, it could also be photons. It doesn't have to be massive particles. And they're just prepared in such a way that they all are directed towards one point in the middle here. And of course, what happens according to general relativity is once the radius of this matter shell is below its Schwarzschild radius, it will form a black hole. The red circle that you see around, you should think of as a huge shell of detectors. Of course, if you do a scattering experiment, we want to capture the debris or whatever comes out of this scattering process. And you should think of this not just as a conventional detector, but as actually a very, let's say, technologically advanced detector that is able to record the quantum state of the incoming radiation. So it will not measure it, but it will actually store the quantum state of, for example, light coming into a quantum computer. So for this purpose, I will draw here, in addition, a little computer. So this is my symbol for a quantum computer. And Bob's task is to record everything that comes out to this shell and store it here. So the first stage, so here is a number, is the kind of preparation state. The matter is prepared and then collapsed. Now, as I said, at some point a black hole will form, and that's indicated by this dashed line, or more precisely, you can think of the dashed line as the event horizon of the black hole. And we know that a black hole will, as soon as it has formed, or even during its formation process, start to radiate. You have Hawking radiation, and this Hawking radiation will now be captured by this shell, and the quantum state of this radiation will be stored in this quantum computer. So the little qubits that you see here, or the little spins, symbolically stand for the qubits that now store the state. So you should think of this like, for example, if you have a mode of the electromagnetic field here coming in, that if, for example, the mode is in this, or let's say the occupation number of the mode will be stored here, but also the coherences. For example, if you have a state that is 0 occupation plus 1 in a superposition, then the corresponding superposition state will be stored. So that's what I mean by the quantum state is captured and it's not measured. So as we also know, Hawking radiation will of course transport energy away, so the black hole will shrink, and I have more and more information from the radiation stored here. And then at some point, the black hole will be gone. And even if there is a remnant, at some point, even that remnant will be gone. And all the resulting radiation will be captured and stored in that quantum computer. And so Q from now on just stands for all the memory content of that quantum computer. So what I've described is this, what, as I called it, the cosmic scattering experiment. And the assumption I want to make is that this process is unitary. So there is no collapse or anything happening. And that's just justified by the, let's say, fact that all experiments so far have not contradicted unitary evolution. But of course, that's an assumption. We are all well aware that there is a possibility that gravity may not be subject to quantum theory. That's something that we need to still test. But for the purpose of this talk, I will make this assumption. And you should see that also as a kind of test of assumptions. So whenever theorists make assumptions, it doesn't necessarily mean, at least for me, that I absolutely believe in that assumption. It's kind of a working assumption to see what we can say. And I think in that sense, unitarity is such a working assumption. So below what you see is just somehow a circuit diagram. So a quantum information theorist would just draw that and say there is some matter coming in, there is some huge process happening over a very long time, and at some point comes out the state of the quantum computer that has this radiation captured. Okay, so far there is nothing worrying or special about that. I think although this experiment is difficult, I think most physicists would agree that there is nothing fundamentally speaking against doing such a cosmic scattering experiment. But now what I want to do is to add some, or make it a bit more interesting by adding a second agent. And so actually, if you ask yourself, why did I have that agent? The agent Bob I had before has two roles. One role is to actually carry out the experiment, but the other role it has is that I always need a kind of user of quantum theory, because I want to be on the careful side and say that I don't want to assume that there's kind of a state of the universe or anything. But what we certainly know is that we, as agents in the world, assign states to quantum systems. And so you should regard the agent also as the one carrying the information or the knowledge about the world. And so when I use a quantum state, I use it in the first, like a priori as a characterization of the agent's knowledge. If you think there is a state of the universe that doesn't contradict that, then that knowledge would just need to be compatible with the state of the universe. But we can always say we in particular can regard an agent's knowledge, or we can use states to describe an agent's knowledge. So now that we have a second agent, and Alice, and she has generally different knowledge because she may have access to different information. And so in this drawing, there's no black hole a priori. So the experiment Alice does is something very standard in quantum information, namely the following. So assume Alice has prepared or has access to these two qubits, which I call R hat and S hat. And these qubits are prepared in such a way that each of them is entangled. So the entanglement is indicated by this wiggly blue line with another qubit, one connected to R hat, which is called R, and the other one, the partner of S hat, is called S. And so the entangled state you could imagine is something like this. For example, a superposition of both qubits being up, or both spins being up and both being down, with equal weight. So of course this would need to be normalized in the usual language, but I will omit normalization here. Now something that is well known, it's kind of, I would say in a quantum information class, it's the first exercise one does, is one says, what happens if I actually apply a measurement to these two qubits in the so-called Bell basis? So the Bell basis is a measurement with respect to a basis where one of the basis vectors of the measurement is actually exactly such a vector here. With superposition, the other one has a minus in between, the third one has up, down, plus down, up, and the fourth one also, but with the opposite sign. So that's a measurement we can do with respect to the four different Bell states. And what is also very well known, and one can calculate with very simple linear algebra, is conditioned on the outcome of that measurement, the other two particles here will be entangled. So the situation will look like it's something, or like after the measurement, R and S will be entangled. I will return to that a bit later, but that's kind of what Alice is going to do. She just applies a Bell measurement to that. But now I want to connect it to the previous cosmic scattering experiment, and the connection I do maybe sounds a bit cruel. I will just let Bob form the black hole around Alice. So Alice performs this experiment. Meanwhile, Bob shoots in the matter shell while Alice is performing that Bell measurement at the inside. The rest of the experiment should be as before. So basically for Bob, nothing changes except that he did the scattering experiment in a particular place, namely where Alice was located. So he will again form a black hole, capture the radiation, and then see what can be done. But what I will now do, let me go back one step, is that this S here, this is the system, one of the systems Alice was entangled with. So let me just for a moment go to the previous slide. So I said before, Alice has access to these two qubits. Imagine that this qubit here, the S qubit, is located somewhere far away from Alice. Alice can still do this measurement. She doesn't need to have access to this and to that. So we can, without loss of generality, assume that this is arbitrarily far away, so far away that it's not within the region that forms the black hole. So this is why I've drawn here the S outside of the whole configuration where Bob does the experiment. So the S is kind of remaining or not affected by this black hole formation. And the same with R. So now the reason why I have these red regions around S and not around R, and also the red region about this, is that this region should indicate to which systems that Bob applies quantum theory to make a prediction. And the reason R is not red is simply I don't want Bob to talk about R. I don't need Bob to make a statement about R. I could include it, but this would just make the system larger about which he talks, but I can also restrict that. So initially, S was entangled with Alice, okay, I should go back again to indicate that. So initially, this S system was entangled with Alice. That was our initial configuration. And of course, if I formed a black hole, we have to expect that still the system S is now entangled with this black hole here, because Alice is in this black hole region. And so as Bob keeps collecting radiation, at some point there will be nothing left here in the middle, and everything is in the quantum computer. So what we would expect is that this string S, this qubit S, is now entangled with the state of the quantum computer. This should not be surprising, because what I'm basically saying is just that because the whole scattering experiment is a unitary process that takes whatever is here at the inside to the quantum computer, the effect is, of course, if something here that was initially here was entangled with S, this entangled thing will now, this entangled information will now be located in the quantum computer. So from Bob's view, the conclusion is this one. S, at the end of the day, will be entangled with the quantum computer state. And this is something that I want to stress that is operationally verifiable. So if Bob indeed was able technologically to carry out this experiment, he could do a test. He could, for example, apply some suitable tomographic measurements here and check that this entanglement is indeed there. Or maybe he could even run a Bell test or so to really be sure that this is entangled. So this is something that could, in principle, be tested. Let's now return to Alice's view. So as I said before, Alice just had these two qubits and applied a Bell measurement to it. Meanwhile, these qubits were far away outside of the black hole. But as I said before, if Alice applies a Bell measurement to these qubits, this will induce an entangled state between R and S. The technical term for this is entanglement swapping. This is actually something that is even practically applied in quantum communication. Namely, in quantum communication, one wants to kind of build entanglement between very remote places. And so you could imagine that if I have entanglement between this and this, so I have this entanglement and I have entanglement between this and that, but I want to build entanglement between this and that, then I can do that by acting only here. And if these may be far away from each other. Here in this experiment, this is not needed, but these two could be far away, and I could still build up entanglement between those. So Alice simply does a very standard entanglement swapping experiment and builds up entanglement between R and S. And so here I think there's nothing disputed. The conclusion is S is entangled with R. So you now see why I introduced two agents, because the conclusions of the two agents, although they are talking about the same experiment, is a very different one. Alice, as I just said, comes to the conclusion that R and S will be entangled. Meanwhile, Bob comes to the conclusion that S and Q are entangled. But S is the same system. So S is this spin that was, or this particle that was outside the black hole. And we have statements seemingly, or I mean, there are different statements, not only seemingly different. S is entangled with R. That's what Alice would claim at the end of the day. S is entangled with Q. That's what Bob would say. Okay, I hope this clarifies the notion of agents, because we just applied the theory, quantum theory, and in the case of Bob, connected to general relativity from the viewpoint of two different persons or two different observers, and I call them agents, because in quantum theory, it's kind of think of observers not as purely passive subjects, but as actually, as agents who are active and do something with the system. Okay, now, I drew here this arrow to indicate that this looks like a contradiction, but most people would, of course, say, no, there's nothing wrong with that. These are just two statements and they will have an explanation. And what are the explanations? The maybe first remarkable thing is that it's probably not a consensus about the explanation. I think there's a consensus that there is no problem with the two claims, but there's no consensus on why there is no problem. So one of the I mean, we have two agents making different claims. So obviously what we can do is to kind of declare that only one of them is right. That's one thing we could do. And for example, we could declare that actually Bob's view is kind of the more, let's say, credible view because he looks at the whole experiment from the outside. And traditionally in science, we kind of made the experience that looking at things from the outside is kind of gives us a better picture. That's a kind of classical worldview that led to the kind of heliocentric view already in the past. And we looked at stuff from far outside and said, this gives us kind of a better view. And if you take this perspective, you could just declare Bob to be right. And that's actually what's happening, for example, if in gravity, if you apply ideas from holography, because if you do holography, you take the boundary as the relevant thing, like the boundary theory is kind of the trusted theory. The boundary theory corresponds to the view from outside. It's very hard from the boundary theory to say what Alice actually would observe. The boundary theory would really correspond to Bob's view. So therefore, one could say that, and this is a very rough explanation, but that holography type ideas lead to the conclusion that this kind of contradiction is resolved by just declaring that Bob is right and something must have been wrong with Alice. However, others would say, no, both are right. And they would say, we have this complementarity. Is there a question?
Yes, there is a question from Madrid.
Okay, yes, sure. Yes, please. Unmute yourself and
Francesca, Carlo, who?
maybe in the meantime, I'll just briefly start to explain the other view. So another view one can have is to say that both Alice and Bob are right. And this is something that would be known as, or is sometimes called black hole complementarity. One would say Alice and Bob would anyway never be able to communicate again because Alice was in the black hole, Bob was outside. So it's okay if they make different statements and they're just on kind of complementary parts. And that's sometimes called black hole complementarity. So that's kind of the view that both statements, Alice's claim and Bob's claim, are perfectly fine. Okay, so maybe you can try it again with the question.
A couple of questions, but
yes, I'm very happy to take them because this is certainly a point where I would expect questions.
Okay.
Can I ask a question?
Go ahead.
Please go ahead.
I have just one question. I mean, simply the order of these actions that happens. Are you considering the statement of Bob after the evaporation of the black hole or before? And
okay, yeah, that's a good question. So you're basically asking about the timing of
exactly because
yes, that's a very good question, and I will actually return to that briefly at a later point because that's kind of indeed something to worry about because I made this statement so far. The idea is that these are statements that should be valid after both parties executed their task. So Alice's task was just to do this measurement, and the statement is a statement she would make after she has performed that measurement. And for Bob, it's a statement he would make after he has collected all radiation. So it's kind of a late time statement in both cases. But there is some problem. How do these two late times relate to each other? And I will return to that question.
Thank you.
And next was, first actually was Francesca.
We were disconnected for a moment, so I may have missed the last. So let me wait and see the discussion. I don't want to repeat something that's been said.
Okay, good. Yes.
Sorry.
And
okay, so
there was one more question by.
Oh, yes, sure.
Hi, thank you. Just a quick question. You said that Bob doesn't take into account the qubit R. But in principle, R is entangled with the computer and with S. So if you trace it out, maybe that hides the entanglement between the computer and S. So in Bob's perspective.
Actually, if he didn't, so if he would also consider the qubit R, then, so I just left it actually away kind of for simplicity, but then the final situation would be that we have here an additional qubit, R, and this qubit would also be entangled with the quantum computer. That
right.
The full analysis would give that. So it's still true that S is entangled with the quantum computer.
Okay. But if you throw away R, in principle, S and Q wouldn't be entangled.
No, here, because so if two systems, like if I have this situation here, that two systems are entangled with the quantum computer, if this is maximal entanglement, and it would actually be, so then it's necessarily the case that they are here entangled with different parts, with different subsystems. So therefore, if I ignore one, it's still true that the other one will be entangled.
Okay, thank you, that's clear.
Yes. Thanks for asking the questions. I hope this clarifies that part. Okay, so the point so far is just to say we have a situation where two agents are making different claims, and if you ask, let's say, if you look at what do people in the community say, in particular in the gravity community, they give different explanations for why this is not a problem. I think none would say this is a problem. They just have different explanations. You see, this is very different, saying Bob is right from saying both are right. Now what I want to do is to look at a very similar thing that has nothing to do with space-time or gravity, but is kind of leading to exactly the same problem. It's a very simple, let's say, analog. We just have now still Alice, and I call her now a friend, because what I'm doing now is to look at a Wigner's friend scenario. So if you don't know what it is, it's kind of just defined by what I do here. You have an agent, and the point is that this agent is assumed to be in a perfectly isolated lab. Perfectly isolated means from the view of the outside observer, whom I call Wigner here, but this takes the role of Bob, this lab evolves unitarily. So that's just what quantum theory tells us about closed systems. So it's now, so I will still have the same setup, that the friend has two qubits she could access and apply a Bell measurement to them, and each of the qubits is entangled with a qubit at the outside of the lab. The other component which is important is because, as I said, this is a closed system and it evolves unitarily, I can in principle, or if one had very advanced technology, undo the unitary. And I mean, it's questionable of how to do that technologically, but again, in principle, there's no fundamental obstruction from quantum theory that tells us we cannot undo a unitary that happened in the world. And so I will just now again analyze this very simple experiment. So the experiment just consists of Alice doing this measurement, or the friend doing this measurement, and Bob undoing the unitary at the end. I will analyze that from both agents' viewpoint. So for Alice, she's in an isolated lab, and I will just analyze it up to the point where she did the measurement. So she has these two qubits, actually the R and S, R hat and S hat that she measures, and as before, what happens is entanglement swapping. So quantum information theorists would draw it like this. So time here goes to the right, and what we did is we had these two qubits, which are now, each qubit now corresponds to a wire of this circuit diagram. So the initial entanglement is indicated by this line. So this just says initially S and S hat were entangled, and R hat and R are entangled. And if you apply a Bell test and condition on the outcome of the Bell test, then S and R will be entangled. So it's important that I condition on the outcome. But Alice, that's why I need Alice. Alice sees the outcome and makes a statement based on the observation of the outcome, and her statement again will be S is entangled with R. For Bob, it looks very different. Bob looks at this whole thing as one big quantum system, the whole lab. And this big quantum system, by construction, is entangled or has one qubit at least that is entangled with S. Like before, I could also draw the entanglement between R and some R outside, but I don't need it. Now, if she undoes the operation, this entanglement that is here will just transfer to entanglement to the output. So this looks like this as a circuit diagram. There was entanglement between the outside S, outside of the lab, and the S hat, which is in the lab. Now, the operation in the lab is just some huge unitary that involves, of course, whatever is in the lab, which includes Alice and all the equipment of the lab. And then by construction, Bob applies the inverse unitary. So everything is returned in its original state. And because everything was returned in its original state, in particular, S will be entangled with Q. Now, you see, we have still two different statements. One statement is that Alice would at the end have said S is entangled with R, and Bob would say S is entangled with Q. And again, like in the black hole case, there are a lot of different opinions how these differences should be explained. And I'll just give you two of them. So one of the explanations, and this is, you now see the similarity to the explanations before. One is to say Bob is always right. Bob is the outside observer. He has the correct view. And that's kind of the many worlds view, one could say. In many worlds, you say, you look at everything from the outside, and that's the correct quantum descriptions. The internal observers, Alice, in this case, they exist in different copies, and of course, there's an Alice seeing that or that, and they are, of course, both okay, but the real thing, like the ontic thing, is the wave function of the universe. So that would kind of give a preference to Bob in some way. Then there are the relational approaches. I would call them the more modern approaches. And this includes, for example, relational quantum mechanics, but also subjective approaches like cubism. And they would say both are right. These are just relative statements that we are making. So in particular, a subjective viewpoint would be that to say that because they're different agents, it's perfectly okay if they make claims relative to themselves, which are different. So we have two explanations. Now comes maybe the most important slide in the context of having this seminar series, because WOST, as you know, stands for without space-time. And so what you can see from what I said so far is that we have two very analogous situations. The left one was the experiment involving space-time. It was a gravity experiment. And the right-hand side was a very abstract quantum information experiment. Of course, it happens in space, but space is not modeled. The whole description here is kind of very abstract, talking just about circuits. So there was a circuit diagram. Of course, there's some time in the circuit, but time is also discretized, just a few time steps. So in a sense, we can say on this side, we abstracted away space-time and are looking at things from a, let's say, really highly abstract quantum information theoretic viewpoint. And the question that I would now like to pose is whether these two communities that study these two different experiments, so these are different communities. Of course, there are some people in the audience here that are very familiar with both sides, but I think generally the majority of people working on quantum gravity look at this and are not aware of the Wigner's friend experiments, and vice versa. Many working in Wigner's friend are not looking at the kind of gravity thought experiments like this. And so my hope is that by connecting these two, one can learn a lot from each other, because both of them have been studied intensively, and there's a lot of interesting and also insightful literature on both sides on these. Let me first point out the kind of obvious from what I said so far. So these arrows should not be taken too literally, but you see kind of there is some similarity, because in the holography picture, this was giving a preference to an outside viewpoint, and the same happens for the many worlds picture. And you could see that very concretely in how one explains the difference between Alice's and Bob's view. And you could say the black hole complementarity, which gives both agents the same right to be correct in their statements, is in a sense connected to the relational approach. So again, I don't want to claim they are the same. They are just the conclusions on who is right, what should we make out of these statements of the agents are similar. There are also major differences. And one of the differences, and this is now connected to the question that was asked before, is how time is treated. And so one could say in the gravity case, we have a highly non-trivial space-time background, and I think the community doesn't even agree on what it is. Of course, the space-time background, the geometry is very different. For example, if you look at a picture that involves remnants, like in loop quantum gravity, or if you make the claim, for example, that the central dogma holds and there is no remnant, this has very different consequences. And so there's no consensus on the causal structure between the different research communities in quantum gravity. In the case of Wigner's friend experiments, one could say time is not mentioned usually, but it's kind of implicit whenever I have a circuit diagram that if I run a computation, there is kind of a clock on the wall next to the quantum computer that kind of indicates time. But there's also some difficulty there because if I do a Wigner's friend experiment, one could say that I'm kind of also reverting time for Alice. That would be a natural view that I think has been expressed by many authors in the past, that if I look at Bob, who is at the outside, for him, time passes as he first lets Alice do the measurement and then undoes the measurement. Time will just progress. Whereas one could say for Alice, if this undo operation is applied, it will, of course, undo the internal state of Alice. And if we identify Alice's clock somehow with her internal state, this will result in her time running backwards. And that's kind of indicated by this line that this time 4 could correspond once again to time Alice being 0. I don't want to now advocate that this is the right view. I just want to clarify that there is a non-trivial also some non-trivial questions about time in the Wigner's friend. In black hole physics or in gravity, the situation is much better studied. And even if you have just an eternal black hole, which I think everyone agrees on, we have very different notions of time. So what you can see here is a space-time diagram with a world line of Bob who stays outside. And here is the event horizon. And for Bob, the natural way to measure time would be time slices as indicated here in red. So time kind of bends, and infinite time would kind of be a line that is almost parallel to the horizon. That's a natural choice. I mean, I'm just saying natural choice. This is not necessary. That's kind of a convention. But for Alice, it's kind of more natural because she's freely falling to have a time that just slices space in the way I indicated here. So the point here is also that Alice and Bob measured time differently, and so we should take that into account. So that's certainly a big difference between black hole salt experiments and the Wigner's friend salt experiments, that we think differently about time. But now I said we want to learn from each other. So let me briefly explain what we can learn by looking at quantum foundations experiments. And so as what actually we found in the research I did, and here I want to point to this preprint that I've written together with Ladina Hausmann. We analyzed certain black hole scenarios like the Haydn-Preskill protocol or the firewall paradox. And if you want, we took out space-time and tried to see what remains. Is there still something interesting remaining from these paradoxes? And what we saw is that they lead very naturally to versions of Wigner's friend that were already known. So, I mean, I'm not claiming that the firewall paradox will directly lead, for example, to this version of a Wigner's friend paradox that I've developed some time ago, but there is a very strong connection, and I would like in the remaining 5 minutes or so explain this connection. So
maybe it's a good point because I see a raised hand by Marius. Maybe we can just take his question at this point. And
yes, sure, yes.
Okay, thank you, Onion. I was raising it just to be in queue for the question session, but I can just ask it. It's a very naive question, but maybe it's helpful. I just wanted to ask you now that you were saying the differences, Renato, is really basic. What I'm gonna say. So in Wigner's friend, the basic setup is that you have the guy that will do the experiment isolated, right? He's not interacting with Wigner, so that you have parity, so that he goes in superposition with his apparatus that is showing up or down. But somehow Wigner has this God's eye view. He's observing in some sense what is going on, so that he sees the thing in superposition. And I'm not sure I understand what's the analog here in black holes, because I understand that there is like a box, like the horizon, there is the inside of the hole, but it's not, you don't have access to the thing from the outside. So I'm not sure in what sense the person outside
So if I
knows
understand
what's
the
going on.
question
And
correctly,
there is
you're
also
asking.
a one-way communication, right? You can send things in the hole. So
Yes. So indeed, so I mean, the analog, I mean, there is a kind of relation, but it's not, and I think that's an interesting thing. It's not a one-to-one relation. So we cannot just say the black hole corresponds one-to-one to a perfectly isolated box. That's not my claim. So, however, one could now analyze things and say, indeed, the black hole has the property that, first of all, Bob can send in certain things only at the limited time, because Alice will, if one use it from the outside, pretty soon hit the singularity, and then it's unclear whether Bob can still send in stuff to Alice. So that will be in a very restricted time window that he could still communicate to her. But the question is why? So in the Wigner's friend experiment, Bob can still act on the whole lab as a big quantum system. Now, in the case of the black hole experiment, here, because that's why we had this kind of scattering experiment, because everything scatters and will, at the end, at the very late time, even after the remnant is no longer there, be retrieved in Bob's quantum computer. And so then he has all the information. So from an information theoretic viewpoint, he can now still do everything on that system. So in a sense, Bob will have at some point again access to all the degrees of freedom of that information from an information theoretic viewpoint. And so, maybe how this is more closely related is maybe something we could postpone to the discussion. But the point is, I'm not claiming that a black hole is just a perfectly isolated lab, although, of course, there are lots of analogies here. Okay, so let me now say, if you ask the question, what can black hole physics or what can we in gravity learn from foundations? Then I could go back to the very early days of foundation and see what did we already learn from Wigner about foundations. And Wigner made a very, I think, important claim, which is actually, I wasn't almost not aware of that for a long time. He made a connection between kind of the question of what exists and what is communicable. So he kind of says, and you see that from this citation from his famous 61 paper, that he basically defines things that exist as those things we can communicate. So the question he was asking here that is, how can we, or does it make sense to communicate the wave function? So if you think about the scenario I had before, Alice and Bob have different wave functions, and I could ask the question, what if for some reason Alice could tell Bob what her wave function was? Is this legitimate? And Wigner kind of assumed that the wave function should be communicable in some way. Now, in order to discuss this from a more modern perspective, I mean, that was a statement that was a long time ago. I want to make a very important distinction about communication. This is really now an information theorist viewpoint. Communication consists always of kind of two phases, one could say. One is really, let's say, for example, if you hear that talk from me, this is communication. And one thing that happens is that you hear my statements, but you just hear them as statements. So you just know what I said. But now a second stage could be that if I tell you something, maybe something less controversial than about foundations, I could just tell you here that when I look outside, I see trees that are white, that look like it has snowed. So then you heard that I said there's snow here in Zurich. But now, does this mean that you know there is snow in Zurich? This is a second step that you have to make. You have to make the step from hearing what I said to say, this is maybe knowledge you could use to some way, or you could integrate that into your knowledge. So that's just a point that I want to make, that I want to distinguish these two phases. So let me make an example here. So for example, Alice this is a very simple example with only one entangled pair of qubits. Alice could have measured it. So there's a pair of qubits. Alice measures it. Time goes upwards here. And she sees that one qubit is in state up. Then, of course, from that, she can conclude that the other qubit that was entangled with the measured qubit is also up. So she says the density operator is up. Meanwhile, Bob may not have seen this measurement outcome. So for him, the state of this qubit is just a mixed state. Now, let's suppose the two communicate. So Alice could now tell Bob what state assignment she makes. And that's just what I would call the data acquisition from Bob's side. So Bob has now learned that Alice made this state assignment. Now Bob has this knowledge. So he has two types of knowledge. First of all, he has this knowledge that he has a priori, what the state was. And he also has the knowledge that Alice said its state up. And now there is something that has to happen, because Bob has to do something with that knowledge. Otherwise, it's useless to communicate with Alice. And in usual situations, which are not Wigner's friend type situations, the natural thing for Bob to do would be to say, if Alice has obviously more accurate knowledge, I was completely uncertain whether it was up or down. That's what this means. It's equally likely up or down. But Alice told me now it's up. Therefore, I should also think I should acquire that, or I should use that piece of data and integrate it into my knowledge and say at the end, the spin was apparently up. Otherwise, Alice wouldn't have told me it's up. And this is what I call the knowledge update. The precise rule to do that may be a non-trivial rule, some Bayesian update or something, but we need something like that. Otherwise, we couldn't communicate at all. The second stage of the communication would just be missing, and then communication is completely pointless. So this is important, that we need always such a rule. Otherwise, it's really pointless to communicate. We would just hear basically other people saying stuff, but it would have no meaning to us. We couldn't make sense of it if we didn't have this updating. Now, this is a slide I'm just have here. This is almost one of the last, but this is something I want to clarify, because often people say that there is no problem with Wigner's friend salt experiments. And the argument is the following. They say that, and now in these terms that I introduced, data acquisition, of course, requires that Alice and Bob can talk to each other. I mean, this is what we had here. Alice was communicating to Bob. Now, in a Wigner's friend experiment, Alice cannot talk to Bob. In the experiment I've shown, this is just not possible. In both of them, also in the black hole experiment, because Alice is in a black hole, and in the Wigner's friend experiment, she's in an isolated box. So therefore, we don't need to care about the second stage, because already this first stage doesn't happen. Bob will just not even learn what Alice has to tell. He will never hear Alice talking. So we don't need an update rule. There's no point in doing an update. However, conversely, in situations where they can talk, the two agents are kind of in terms of, let's say, if I talk about the Heisenberg cut. So the Heisenberg cut is kind of what separates the agent from the system. They usually can talk in situations where they are on the same side of the Heisenberg cut. That's the usual situation. When we talk about the quantum system, we are both kind of classical, or we consider ourselves classical, and there's a quantum system lying there. This was in the example I had here. So here, Alice and Bob are both considering this as the quantum system, but neither of them treats the other agent as a quantum system. And in this case, they can communicate, but in this case, it's also unproblematic to do an update of knowledge, that's what we do all the time. Otherwise, we couldn't even learn quantum mechanics. I mean, we make sense of what the others do. And so a common misconception is that we are always in either of those. So either communication. So in the cases that would be problematic, like Wigner's friend cases, Alice and Bob simply cannot communicate, so there's no problem. And conversely, if they can communicate, they're on the same side of the Heisenberg cut, therefore it's also unproblematic. But this is wrong, because there are more complicated situations, and I think this is now referring to this SOT experiment that I mentioned, that I developed together with Daniela Frauchiger a few years ago. There we have exactly tried to kind of find some example in between. So the agents can do the data acquisition. So the data goes from Alice to Bob, so to speak. It's actually more complicated, or more parties needed to do this communication. But at the end, the data flows from Alice to Bob. But still, they are on the same side of the Heisenberg cut, or only agents who are on the same side of the Heisenberg cut have to apply the rule of updating. Nonetheless, one runs into contradictory statements. So in other words, one has a contradiction between saying quantum theory can be applied, and in that case, one also needs to apply it to quantum agents. But the other assumption is that, and this is important, that here we have this word classical. If an agent A knows that another, for him, classical agent B knows something, for example, that the spin is up, or that the measurement of a spin gave up, then he can conclude the spin is up. This seems to be unproblematic, but the point is, it still leads to problems. And now we can ask ourselves, this is an insight, like even just assuming quantum theory and the communicability in this sense, these two things are contradictory. What does this mean for gravity experiments? And maybe I should stress one point. Often, or maybe that was my fault, actually, sometimes people said in my papers I claim that quantum theory is contradictory. But I think the correct statement, and I want to use the opportunity to stress that here, is that quantum theory, together with an assumption of how to update knowledge, so some assumption that allows us to communicate, that leads to contradiction. Quantum theory itself is okay, because that would just result in Alice making a statement and Bob making a different statement. The question is really, can they somehow reasonably combine their statements? And the point is, as soon as they try to find a rule to combine the statements, this leads to contradictions. And of course, one may find a rule that avoids that, but all the rules that are kind of known or have been studied lead to contradictions. Now, what's the point? Why I'm stressing this, or why do I go back to this experiment? If we now make this translation between pure foundations experiments and black hole experiments, we find that people have very similar no-go theorems. So I call this a no-go theorem because it says two assumptions lead to a contradiction. But the black hole no-go theorems are much more complicated. They involve also usually something called the unitarity assumption, which is pretty much the same as assuming quantum theory, because I assumed also quantum theory is unitary. But then they have many additional assumptions. For example, they assume the smooth horizon, so that if Alice falls in, nothing bad happens to her. It's also sometimes called the no drama assumption. Then they have other assumptions, like something called the central dogma, which is an assumption saying that the black hole is a system with a relatively small size. I mean, given by not very small, but the size is given by the area of the black hole. That's also an assumption. And then they show that these assumptions give a contradiction. Now, the usual conclusion is that one of these assumptions are problematic. But now what happens is that they also always make a communication assumption, because necessarily they have different agents. I mean, all these black hole SOT experiments involve Alice and Bob, and at some point you need to compare their views. So they have some communication assumption. By the communication assumption, I mean this update assumption, not the assumption that they can physically communicate. That has to be given already. And in the firewall paradox, for example, which is one of the foundation experiments, it's explicitly said how they physically communicate, how the information flows. The data acquisition is given, but what is not explicitly stated is the communication assumption. Now, the point is that if already quantum theory and communication assumptions are known to contradict themselves, it's kind of not clear what this here means. So why we should be interested in adding more assumptions. So in other words, what we can learn in quantum gravity from quantum foundations is that we have to take this communication assumption seriously and not have it implicit, because it may be exactly the point where things break. So in other words, quantum foundations teaches us, and this really goes back to Wigner in a sense, that communication between agents and how to reconcile their views, how to combine their views is a very important thing. We should not just leave to our intuition. We should make this an actual research topic. How do we update the different knowledge? How do two relational views combine? And of course, some rules are known. We know, for example, in the, let's say, expressed in the relational picture, if they are both in the same coherence, if the facts are stable, as one would say there, then they can communicate. But we also want to have more general rules, because in the black hole experiments, the facts don't, or the measurement outcomes don't satisfy the stability condition. And so the question is, how do we still make sense of them? So the conclusion I want to go to is to say that we should really try to see how we can kind of learn from the insights from each other. And I gave you an example of the insight that communication is important, that an update rule is important. And I hope this will, applying that idea that communicate or giving more importance to that communication assumption will give insights in gravity. Okay, that's basically what I have here on my conclusion side. So let me say it again. We have so far in quantum theory usually studied individual agents, and somehow whenever two views were there, we have kind of ad hoc rules to say how they are combined. But we should now move away from these ad hoc rules and take it serious that this is a non-trivial issue, that it's not so clear how different agents' views are combined if they are not on the same side of the Heisenberg cut. And I hope that we can make progress there by just looking into that with a scientific way, in a scientific way, and not see that that's something that is outside of quantum theory and kind of leave that to the kind of vague area. Okay, thanks a lot for your attention. And if you have some, let's say, if you want to know more about this link, I recommend this preprint that I've written that has also many references to work related to that.
Thank you, Renato, for this super interesting talk.
Good.
And so now there are already quite a few questions. Let's see if I can keep track of that. But I remember that there was Sugatu Bose who raised first a hand during the talk. I decided not to interrupt anymore because
I saw there is also some activity in the chat, but unfortunately I wasn't able to read the chat while talking.
Yes, yeah, there's also a question in the chat. So Sugatu, are you there?
Yeah, I'm here. So actually my question got partially answered with the later part of the talk, and it's kind of commensurate with some of the questions asked in the chat as well. But maybe I'll just rephrase. So Renato, so how much importance, so by communication, do you really mean that the measurement process and outcome is also included there in that what you call as communication, right? Because the Bell state measurement is in Bob's frame, kind of he's combining all the 4 Bell state measurements in the quantum computer. Would you say because update requires knowledge? I mean, can you replace your communication assumption with measurement? That's the question, I guess. Yeah.
Yes. So yeah, that's a good question. Let me maybe clarify that. So of course, if we look at the measurement result, we update the knowledge, and I think that's something that is already that's let's say, first of all, a single agent operation, which is very well understood and formalized. We know kind of we have rules that we apply, let's say, daily when we do quantum experiments. If I see a measurement result, what does that mean now for the state conditioned on that result? So that's not the thing that I'm kind of saying we should study more. That's of course important, but that's very well understood. I think what I'm referring to is the update that has to happen once I've received communication from someone else. So like in this example, Bob has received the communication from Alice that she makes that state assignment. And now the question is, what should he make out of that? Should he simply ignore it? But that would be, of course, in general, we don't want, because that would, as I said, mean we cannot communicate. That would be kind of an extreme form of complementarity. We just say everyone else is wrong, I'm the only one who is right. But of course, we don't do that in practice. Clearly, for example, I mean, you could make this very same example with a random coin. I could flip a coin and then ask you, what's your knowledge about the coin? You would say it's equally likely heads or tails. Then I can tell you, I've seen its tails. Then clearly you would not insist that it's still this mixture. You would say, no, I update my knowledge. Now, this very trivial thing that we do all the time is less trivial or is exactly the thing that leads to contradictions in these Wigner's friend experiments, but not in the standard ones, because in the standard ones, the communication simply doesn't happen. Alice cannot talk to Bob, but in the extended ones, there the communication kind of happens, but the update rule has to be applied. And if you apply the kind of naive, I would say, basically such a thing like here, if you tell me the outcome was up, then I just take this as, yes, it's up. That leads to contradiction. So we need to rethink that update. So it's basically the update following data acquisition by communication, but not from the measurement. That's already understood. Okay. So thanks for asking, because I should have made this distinction. It's really about the update after receiving knowledge from someone else.
Okay, thank you. Thank you.
Okay, so then next is maybe Carlo or Francesco, their group.
Thank you. Can you hear me?
Yes, I can hear you, yes.
Okay, thank you very much, Renato. This was, I found it super interesting, super challenging, and you raised a lot of things, and it also was very carefully presented, so that helps a lot to focus on a number of issues. There are two questions I would like to ask, but maybe I should say, just briefly mention the first, or two comments I have, if you want. Very first, go to the first, and can you go back to the couple of slides when you have the different alternatives for in the black hole, the different assumptions
yes.
Before this? Yes,
it was here or so. Yes. Okay, this was the one that combined them. I had an earlier one.
At the end, toward the end, you had unitarity, smoothness, central dogma.
Oh, this one. Okay, I see. Yes, sure. That was towards the end. Yes.
This seems to me a very clean way of posing the question. I mean, everything you say about the communication puzzle, that the situation, it's very convincing. I would say the question, the interesting question I would like to raise is whether what people call the apparent contradiction in black holes comes just from the first three, and also there is a fourth one, or the first three by themselves hide. It is usually hidden that there is also C. Because I would say, but I might be wrong, I would say that U, H, and D are by themselves contradictory. That was the sort of the paper by Marolf and company with about firewalls, and then different research direction discard the central dogma that I would discard, discard smoothing of horizon, which was what holography people would discard. But are you saying that, so let me put it carefully, the question. Are you saying that, no, look, when you're talking about that, you're assuming that there is also an issue about communication, or you're saying in addition to that, there is another kind of puzzles? Because the kind of puzzle that you mentioned in the Peskin and other and the black hole complementarity are not what people usually call the contradiction between U, H, and D.
Yes. Okay, yes, thanks for raising this point. So the way I see it is as follows. So let me first say there are, of course, independent reasons, independent of these experiments, or of these thought experiments like firewall and so on, to reject some of the assumptions. I mean, of course, I know about, for example, your arguments against the central dogma and so on, but this is not now about that. So now what I want to say is about, let's suppose we just look at it from the viewpoint that these are possible things and we want to see, are they mutually consistent? Now, my claim is that if you look at these arguments and you go through the individual steps, then you will find that at some point they implicitly make use of such a communication assumption.
Yeah.
And it's necessary. I mean, it's maybe in different forms. I should maybe say what I stated as the communication assumption. This update is not, it's not always coming in that form. So sometimes it's coming in
that was an answer, Renato. That was very clear. Let me go to, thank you. Let me go to the second question, which is my second issue. It's much more, you know, you said that that's about the communication. That's about what you're coming back as a communication issue. You know where I am, right? I very much think relationally, like Zeilinger, or like people in Cubism in that context. So there's something I'm missing, and maybe it is related to Sugato's question, which is the following. I would say, and I'm not sure you would say the same. It seems to me you would not say the same. That's what I want to probe you. I would say that knowledge is not something unphysical. So when we say Alice thinks that, we are saying in the brain of Alice, there is some configuration, which is a physical configuration, which can be described as a physical system. So there is not something else that the state of Alice in her knowledge. Her knowledge is just her state. So I would say, in fact, that was one of my primary assumptions that you seem to contradict, and that's why I failed to understand you, that any communication, anytime Alice says something to Bob, or Bob learns something from Alice, is from the point of view of quantum measurement. So every interaction is a quantum interaction. So if this is the case, then we know exactly what happened, because when Bob asks something to Alice, is making, from the perspective of Bob, a measurement, is projecting the state. It doesn't. We don't need an extra story about communication. It's just standard story. And to Alice, knowing something is what we usually describe, like the apparatus knows about. There's a correlation between, and etc. etc. Now you seem to willing to discard this simple answer. And you often in your papers and your talk say, oh, but if it was so, we could not do science, we could not trust our friends, we could not, which seems to me very, very weak as an argument. If you have written a paper, Alice can do science with his friends, even if she's quantum mechanical. So why don't you go that way? Why do you insist in thinking that what Alice knows is something else, that just a variable having a value, which in quantum mechanics can be in a superposition?
Yes. Okay, yeah, that's a very important point. So let me maybe first say that I would agree with the statement that I could also treat the communication that comes, or Bob could treat the communication that comes from Alice just as some, let's say, physical system that comes in and he measures that, and then doesn't actually treat Alice as an agent. It's just some physical system. So that he could do, and there's nothing that speaks against that. I have nothing against that. So that I absolutely agree that he could do that. Now, however, the point is the following. So this will kind of be, in a sense, a single agent theory, in the sense that I consider myself as an agent and everything else is just a world that is a big physical system. And I think that's very safe and nothing goes wrong. But I think what I want is, I demand more from my theory. And this is really an additional demand. And of course, someone could say, maybe I demand too much. But let me illustrate that demand. Let's, for example, say, you now tell me something about the weather in Madrid. Now, of course, I could just treat you as kind of a very elaborate measurement device that takes as input the measurement, convey that to me, and I don't treat you as an agent, so to speak. You're just a physical system. But now in practice, let's say in the way we actually apply, let's say, reasoning is on a different level of abstraction. And it's on the level of abstraction where actually I want to treat you as an agent because you have already, for example, acquired a lot of different knowledge. And I don't even know how you acquired it. I only know that you correctly acquired this because you trusted you. I trusted you, or I trust you. And then you kind of act really as an agent. And I have very little information about you except that you are an agent. So maybe a good example is someone who writes a book. I mean, you wrote many books. And of course, I cannot reproduce how you wrote this book. I would have to model you as a physical system. That would be enormously complicated. But at the end, I read your book and I take the knowledge from that book as reliable knowledge, or any book on quantum theory that is serious. Now, the question is, in other words, what I want is I want agents to be able to communicate or to exchange knowledge on the abstract level, and this has a kind of an advantage. And this advantage, I think, is without that we couldn't do physics. If I had to, let's say, learn quantum theory or anything about nature by treating everything I receive as a direct physical system and not treat that, what I see, as agents who have already processed that and compressed the information and then transmitted it to me, then I would have to redo all the work. I would basically have to model everything myself. So now this sounds like a pure practical difference, because we could say in principle, I could just model the whole world as a huge quantum system and do everything as well. But there is actually an additional difficulty, namely that even me as myself, I have to trust my earlier self, for example. So even that communication would be problematic. That's also something that I processed earlier. For example, I convinced myself yesterday about something.
Wait, Renato.
Today I just know that. Pardon?
No, but relation quantum mechanics and the way, I don't know, Zeilinger or Fuchs, not just my own way, a variety of, is not what you're saying. I mean, we know that we live in a large decoherence domain, and we know that we can just put the Heisenberg cut somewhere, and I don't have to close myself in a solipsistic myself to use it. I know very well that I can consider classical, thanks to the coherence, a lot of system and books and experiments and newspapers and radio things. So I can do all the science of the world, being careful that sometimes interference effect might come in and I have to worry about those. So one thing is to do that to get knowledge practically, and one thing else is to say it has to be at every level of precision, which is what you're assuming. So you're putting two alternatives. One is that I treat everything quantum mechanically and nothing classically, okay, or there is something which is ultimately classical and not quantum mechanics. And I think this misses what we actually do. What we actually do is to treat a lot of things classically because it's a very good approximation and allows us to make good physics, understand a lot about the world, and talk and go through our life usually. But then we be careful that sometimes goes wrong. And that's fine, because sometimes with respect to us, there are interference phenomena between you, Renato, being one state and you, Renato, being another state. What's wrong with that?
Yeah, I think, okay. I mean, I agree with the statement that we could do that in principle. Now, I think what I disagree with is that we are ourselves in the actual world a bit like Alice, not like Bob. We are somehow in the middle of the universe. We only see a small part. So I would say, let's say my answer would be, we don't even have the chance to be careful. Of course, if we wanted, we want to be careful, but we simply don't have that information in the following sense, that if you look at Alice in these sort of experiments, Alice will just, let's say, speaking in a kind of many worlds language without trying to imply how to think many worlds, but Alice is just in one branch. And we now, as I talk here and get information, I just get information about one branch of the wave function. So I simply I fundamentally don't have the information that would allow me to take into account all the interference effects that would be seen from an outside observer. Now, I think what I have an issue, or what I would say, is that if these, I mean, first of all, maybe that was clear implicitly, I'm not really, let's say, supporting the views that an outside view is better than an inside view. So I think as physicists, we only have the inside view. We are really more like Alice than Bob. So therefore, I want to have rules to do physics which can deal with the very limited knowledge that Alice has and doesn't need to take into account the outside Bob's knowledge. So in other words, my worry is that I couldn't be careful even if I wanted, because I simply don't have that information. As Alice, I have no other chance than kind of saying, we are in a certain situation with limited information. How can I still make sense of the communication? Maybe the answer is we cannot, but that's now a personal opinion, that I don't believe, because I think we were pretty successful in doing physics so far, and we had always Alice's perspective. And so it's more like a question of, can we do physics with the limited information we have as being part of the universe and not an outside observer who sees all the phases between the different branches and so on. So
I don't want to monopolize the conversation. I want to let you.
Yeah, maybe that's it. But maybe let me just summarize. So as I said, I have nothing against looking at or like this measurement view. So that there's really nothing wrong with that. But I want more, because I want that I, as an inhabitant of the universe with very limited information, can still do physics. And I think the problem is with the measurement-based view, I would need to know too much that I don't have. So I couldn't make the usual inferences. I could never be sure. I would have to rely on being in a typical situation or so, but I couldn't actually fundamentally make the correct statements with certainty.
All right.
So to be continued. Thank you very much.
Yes, I mean, this is a very interesting discussion.
Yes,
and,
I propose
yes.
We'll give the opportunity to others to ask some questions, and if there is time at the end and interest, we can revisit this subject. I think Nathan was next, then Fidel, and then maybe me or Glenn. I'm not sure. So we'll say that. But Nathan.
Hi. So I would like to ask about a very simple question about irreversibility. So there is the stance that says that if a quantum measurement can only be made if it is irreversibly registering something, and you don't even seem to mention that as an assumption. So,
Yes, I didn't mention the assumption. So in this view that I presented, everything is relative to the agent. So for Alice, that measurement would indeed be irreversible, because she's, I mean, you can see it like and she's from the outside getting entangled with the system. And so she cannot make the decision to reverse the measurement. So if I just take Alice's view on the world, so to speak, and as I pointed out at the beginning, I'm always taking an agent's view, I would say a measurement is irreversible for Alice. But everything is now in this view relative to the agent. So this does not necessarily contradict the view one could have to say that for Bob, the very same operation that for Alice was an irreversible measurement is for Bob a reversible operation, because Bob has by construction here the potential to actually revert the measurement. So in other words, in this view that I presented, I kind of take a measurement as a relative notion. Now, this is not contradict. So I see that as kind of the more careful view, in the sense of if I say something is potentially a priori relative, then this doesn't exclude that at the end there's a rule which says everything should be the same for everyone. So I'm not trying to contradict the view that is absolute. I'm just saying that a priori, already assuming that there is an absolute notion of reversibility would be a very strong assumption. So I kind of say that a measurement is only defined relative. And so the irreversibility is relative as well. So to summarize, the measurement is irreversible for Alice. Alice's measurement is irreversible.
Okay.
All right. Then Adele.
Okay, I think I was there. It's a very, very quick comment. I didn't know also this statement of Wigner that something to exist has to be communicated. But then the real line doesn't exist. Because in order to communicate a number, I should, if it's a rational, just give the number. Otherwise, I have to give an algorithm these are the computable numbers for which there is an algorithm. But algorithms are countable; they are Turing machines. So paradoxically, the whole line, according to this point of view, a bit extreme, doesn't exist because it cannot be communicated. Only some dense subset. So okay, we are. Here, people saying that space-time doesn't exist, so we can start from the real line and then extrapolate. So it was just a quick comment on this statement. It of course has to be put in context.
I have an answer to that. So, yes. Of course, I don't know at all what Wigner thought about that. I just have this citation which concerns the states. However, independently now of what Wigner thought, I would agree that this criterion of reality being communicable would indeed exclude real numbers being real. And my friends in Geneva, in particular Nicolas Gisin, has written a paper with exactly that title, Real Numbers Are Not Real. You may have heard about that.
Yes.
And where he basically makes an argument along these lines. And I think for me, this makes also a lot of sense. I think this is indeed kind of compatible with the broader philosophical viewpoint that real things one could define reality by being communicable. At the end, it's a definition in a sense, but I think it's a very sensible definition.
It goes together with the fact that an experiment will never give you a real number, but will give you a number with a certain number of bits and an error. So it was just a quick comment that came while you were talking. Thank you.
All right, and let me not abuse my position as a chair. I give the word to Ghislaine Fournier.
Thank you very much. Thanks for the excellent talk. It was very exciting. So the take-home message for me was this part where you show the two sides, where with the black hole on one side and then the isolated lab on the other side, and the analogy between the two. And so I had a question. You briefly mentioned the possibility of remnants, I think, at some point. So there's people who think black holes completely evaporate, but then there's the possibility of Planck stars where there's still going to be remnants. And I was thinking of how that plugs into this if these two possibilities correspond to some interesting insights when you connect the two. Is it something that you've already thought about, or maybe it does make a difference if there's remnants or if it fully evaporates?
Yes, it does make a difference. So, I mean, I take here a kind of neutral perspective and say we can just go through the different options. And if there are remnants, this changes so maybe I'll briefly show this diagram. So here I've just shown the causal diagram of an eternal black hole. This doesn't show the part where it's evaporating, but the way this diagram continues at the point, let's say, where it evaporates completely would look different depending on whether you are, for example, in loop gravity and have a remnant, or whether you, for example, follow these, let's say, gravitational path integral calculations where people came up with the, let's say, what I call the central dogma. So the time evolution, let's say the relation between the different times, in particular between Alice and Bob, would change. And this has an impact also on the abstract side. So when I made this relation, when I mentioned the relation between the firewall paradox and my thought experiment with Daniela Frauchiger, I was here using the assumptions that enter the firewall paradox, which is the central dogma, which excludes the remnant. And so this analogy actually only works in that case. And so if one has a remnant, it's probably analogous to another different thought experiment, which has a different structure, or there are different access. So it changes which information is accessible when to whom, because it actually changes when can Alice and Bob exchange data in a sense. And so what I think Mario asked at some point, so there is, of course, communication from the outside into the black hole, but only for a certain time. And then one can ask, can later Bob still talk to Alice and so on? And this all depends on that structure. So this relationship, in other words, depends on very strongly on the causal structure.
Thank you.
Okay, and well, thanks, Renato, for this very interesting, very provocative presentation. I wanted to ask you about the role, specifically how you see this role of making this connection to gravity in the following sense. I mean, clearly you have shown that we can present these types of paradoxes as analogous, or in a way there is a certain mapping into the more, let's say, traditional or standard paradoxes, Wigner's friend, where there is no gravity assumed. So my question is, like, is there anything specific? Is there an additional challenge now that we're facing when trying to reason about these things in the context of gravity, or is it just a kind of an instance of the same old paradoxes that show the measurement problem?
So I see it rather than a challenge, maybe more as an opportunity in a sense, because let's say one of my points that was also related to the question that Carlo asked is that so far this communication assumption was implicit. So this means people in the gravity community, for example, those talking about firewalls, so that as communication as so obvious that they didn't even mention it or recognize it as an assumption. So in the sense, connecting these views shows that certain things that looked so obvious they were not even stated explicitly are assumptions. And this, I think, may also be true in the other direction, because when we talk about Wigner's friend, we usually ignore any aspect of time or space, or also reference frames, for example. And I think this analogy should make us aware that we should include this, that maybe our models that we are using for these paradoxes are maybe too simplistic, because the quantum information view, which is the one that, I mean, usually Wigner's friend paradoxes are phrased completely in a quantum information language, but the quantum information language is very, very abstract. It ignores time basically and space anyway, but time is just some discrete thing. So I think what this relation teaches us is that we should be careful in not ignoring aspects that could help resolving it. And so personally, for example, I'm very convinced that to resolve issues like this, to, for example, decide when is communication possible or not, has, for example, to do with the presence of reference frames. I mean, they don't explicitly appear here, but it's just this connection makes it clear that spatial aspect and also what is time and so on are very relevant. And I think I alluded a little bit to that when I had this picture with the clock. So that's, or let's say this timing. So that was this picture here. And I said, usually we don't even see these pictures. So a very first step to include knowledge from gravity is to say, actually, we know time is relevant, so we should also model the time explicitly. What does it mean? It means we have to model the clock. The clock, now we have a lot of knowledge from those working on reference frames. The clock is a reference system, but we should include that explicitly, because if we revert the unitary, that will have an impact on that reference system as well. So in that sense, my answer would really be, I see it more as an opportunity to transfer knowledge from one side to the other. And this knowledge could just be knowledge about what could be stuff we were ignoring in our abstraction.
And maybe this is very new, but like perhaps because I'm also not sufficiently familiar with the exact paradox in the case of Preskill and the Haydn's model. But there, there is this issue of there is a space-like hypersurface that we identify, and we can, at least geometrically, where there seems to be these two incompatible types of information that we can think about it in this. Of course, they cannot be accessed by the same observer, but is that the correct understanding that I have? And is this different? Is this something that we do not get in the more traditional Wigner's friend setup? Or do you think that maybe this just gives us an idea of how maybe we can kind of incorporate ideas about causal structure into the analysis?
Yeah, I think there was on both sides kind of a development of making things more operational. So in what you mentioned is Hyde and Prescott, they were indeed talking about a QISS, like a foliation of space-time with QISS slices, and talking about the state of that on the different slices. And then at some point one realized that maybe that's too abstract. We should be more operational and not just talk about the state on a QISS slice, but actually information that is really accessible to the agents. I think this development happened, and the firewall paradox is, for example, in that sense, much more operational. There, it's achieved that there's at the end an agent who has all the information and can test, for example, the entanglement. And I think the same is true on the pure, let's say, Wigner's friend side. So maybe remember I stressed the fact that Bob could actually operationally test the entanglement. And I think so what is actually operationally accessible and what are just statements that are, in a sense, never operationally testable and purely mathematical in that sense. This distinction is important, and I think the trend on both sides has been towards being more operational. But I would say that's kind of independent of the connection. That was just on both sides recognized that being more operational means being more careful and not neglecting things that we shouldn't neglect. And so my view is that to be like this connection helps us to be even more operational, in the sense that things as I said before, that we didn't model beforehand, like the clock on the wall in Alice's lab, should also be modeled explicitly as a reference system, for example. And so in Hyde and Prescott, you could do now the same and ask yourself, what does it really mean to, what does it mean that there is a state on a QISS slice? What measurements could you make? What would be the references for that measurement, and so on? But I cannot give you, I see this really as a very open field now. And I think my contribution, I would just see as making us aware that there are two communities which are working, in a sense, on very similar questions that are more similar than we thought, and just giving examples of how we can learn from each other. But I would expect we can learn much more if we take this serious.
Great, thank you. And Lucian Hardy, Lucian?
Yeah, thanks for the talk. I really enjoyed it. I especially enjoyed the inverse VOST map.
It's probably the next project after VOST. We have VOST to the -1.
Yeah, I think that's a good idea. Yeah. My question is so that when you were setting up this kind of contradiction, the sort of things you were considering were questions like, what is entangled with what? Like, is system A entangled with system B type questions? And my concern is whether that is the right kind of thing that people should agree or disagree on. It could be that it could be that whether A is entangled with B is not itself an objective matter. I'm thinking in particular of in this work on quantum reference frames that Flaminia et al. Did. Then that kind of statement depends on what reference frame, what quantum reference frame you're in.
Yes.
So so is that a concern, or do you have a?
Yes, I think I would share your concern. So I would also say that clearly we have to be aware of the fact that statements about states are very dangerous. And actually the reason, that was even one of my motivations at the time when I did the work with Daniela Flauchiger, because there the contradiction doesn't arise from statements about states, but statements about measurement outcomes. And actually, the motivation was really exactly that concern. So maybe for states, we are in much less certain terrain. But even when we are now talking about outcomes, these could be relative to references. So what you just said about the relevance of reference frames, I would say is anyway very relevant. I mean, they're anyway very relevant because in this paradox that I mentioned here, when I talked about my work with Daniela Frauchiger. So this is really in contrast to what I presented at the beginning of my talk about outcomes. So this is supposed to be an outcome. And so still, of course, if we say someone says the spin is up, this is relative to a reference. So that's why I think we should take this very serious and be aware that these are statements that are relative to a reference and see whether the problems may arise from the inability of two agents to share a reference. And this could actually be interesting because if one agent is in a black hole and the other not, for example, it's not so clear that they could even in principle share references. Or if one is only in a quantum computer, what happened with the reference? So I think, in a sense, I would just agree with what you said, that these are concerns one should have, and these are possible ways to get more insights on what's going on, to question exactly these things, like is it sensible to talk about the state without explicitly stating the reference, but even for the outcomes, like even in that case, I think we should take reference frames very seriously.
Okay, yeah, thank you. Thank you.
Okay, I don't see any more raised hands in the chat. If there is
actually, I have to say, unfortunately, we have oral exams, and now there are some students waiting in front of my door.
It's just the right time, actually,
have to
wrap
take
up.
their exams, so I have to stop soon.
Yes, great. So let's thank our speaker again, and goodbye, everybody.
Thank you again. It was a pleasure, and thanks for the many questions.